Hello. Hello. I believe this is working. This is indeed streaming. Hello. Oh, hold on. Gotta make sure we're running this thing. Okay, now it's running. Excellent. Hello, how you doing? This is JF here, and this is Carlos.
Hi, I'm kind of the guy that works with the magic of electronics here.
Ah, yes, it is a magical thing, isn't it? And we have Aaron on live stream right now, or at least live chat. No. I'm not sure if we're coming through okay. Based on what my system is saying, yes, it is. I can hear myself actually right now. That is being paused, so no any problems here. Okay. So long story short, we're going to be doing a demo. We pre-recorded the entire process of printing and picking placing, just to speed up some of the more boring moments and get something down to a small, easy to use video that you can see. And we're going to explain the process of printing. We're also going to talk about Carlos about why we made this, and I'm also going to go through some tips and tricks about how we made this circuit work and how, in some ways, it can help you in your own pursuit. So, what's the story behind this circuit? This guy. What's the story behind this thing right now?
Okay, so this circuit is it's a power source. It technically provides two voltages. It provides a regulated source for 12 volts and a regulated source for 3.3 volts.
Mm-hmm.
And the reason why we ended up designing this was we had a larger board that had several components. It had sensors, it had a microcontroller, it had some motor drivers, thermistors, readers, and drivers, and all sort of things in there.
Mm-hmm.
And we ordered this board from a manufacturer because it was supposed to be a close to final design.
Mm-hmm.
And once we got it, we started testing, and we realized that the power source that we had designed before wasn't giving us enough juice. So essentially, the regulators were heating up, and in the end, they will essentially blow and burn.
Fireworks, which
fireworks.
is no one like. Some people like fireworks, but controlled fireworks, right?
Yeah, exactly. So this board came about since we have something that works mostly except the power source. We very quickly went to the workbench and started designing something that would work.
Mm-hmm.
And we changed essentially inductors and capacitors to make sure that their relationship and the frequency we were switching this regulator was fast enough to provide the power that we needed.
Mm-hmm.
And then we were faced with two options, right? We could either have like this mess of cables, wires going here and coming back, right? Or we could, have that and connect it to the board. Essentially, we will cut out the lines for power and connect this thing instead. Or we could redo the whole board, remanufacture it, wait for 10 days to get it back, or 5 days to get it back, reassemble it, and hope that everything is okay and go for it. There's a third option, which is what we went for. So once we had something that was working, the design was working, we kind of verified some, by connecting some wires here and there. We designed it in KiCad, and we went and printed it. And we had a working switching board that can provide us about 3 amps per channel in less than a day. So it was a very quick process. We replaced the 10-day process for a 1-day process, and we skipped all the mess and cables like coming out of the machine. This is a machine that we are actually using for demos and like development, so we don't want to have a messy machine either.
Yeah, and I mean, getting these kind of boards, how much would it have cost to actually get this board made?
So technically, if we just build this board, the one we have now, that could have been probably, I don't know, I would say $40, maybe $40 to $60. It's a 2-layer board.
Mm-hmm.
But if I had done what I was hoping to do at the beginning, which was like creating the whole board again, like the complete board, that would have been much more expensive, right?
Right.
I already had the microcontroller working. I already had all the capacitors working, all the sensors, all the switches, the drivers, right?
Mm-hmm.
So recreating that board could easily be like done for what, I don't know, at least $200 because I have a bunch of parts already in there. Right? So this is by far way cheaper and faster.
Yeah, and I think speed was kind of the key element. Like we have another project going where we're waiting for boards, and they've been delivered to some mysterious person.
Yeah.
We
Right
don't
now
even know
we're trying
where-
to solve the mystery of the missing boards.
Yeah.
Yes. So indeed, it's a matter of time. It's a matter of cost, but it's also a matter of testing the components that you're going to use in the end, right?
Mhm.
If you build this board on a let's say you want to build it on this white breadboard, right? Where you just connect components.
Mhm.
Most likely you are going to end up using essentially true hole components.
Yeah.
Or if you have a high frequency switcher regulator like what we have in this case,
Mhm.
you will be in a high frequency range.
Mhm.
And then if you have long wires, we all know that that will create noise and will create all sorts of weird effects that we
Mhm.
don't want. And the only way to figure out if your design is working properly is by laying it out exactly as you will lay it down in a board, in a printed circuit board.
Yeah.
And keeping the components as close as possible to get the closest result as possible.
Yeah.
So this is the best way to simulate a design that you're going to use in real life.
So you can't use things like Spice LP or anything like that where you can simulate the board beforehand. Why wouldn't you just do that?
You
Some
can
people have
absolutely do that. In the end, it comes down to because different components have very different types of changes between one and the other, like differences in like the impedance, the maximum frequency they can run on, the maximum power they can drain. So once you make up your mind on which component you're going to use,
Mhm.
you can indeed simulate them and get something called the Spice characteristics. And you can load them in Spice, but you will never be sure that it will work until you actually make it work, right? So it's kind of, I mean, you will always find this bridge that you will have to cross eventually, where you have to build your prototype and make sure that the design is correct.
Okay. And so you've actually seen situations where you've simulated, and then the board is
Yeah.
completely different.
Yeah, absolutely, because all the components that you have in a board have a certain degree of tolerance, right? So
Right.
you go with as simple as resistors that can go from 0.1% tolerance to
Mhm.
10% tolerance, and if you have something that you need with very high accuracy, 3.3 volts, let's say,
Right.
and you're getting 3.20 or 3.22, that may not be enough for your application. So sometimes in the end, you kind of need to know what you are facing.
Mm-hmm.
You can simulate a lot and you can get really, really close to the values.
Right.
In the end, you will only see the real result after you have mounted it on the board, because there's a series of things that play around, like, depending on your routing, if you're having like crosstalk, if you're doing like high frequency or lower frequency, or like I can think of different things that could affect your design depending on how you lay it out. As simple as how much space do I need?
Yeah.
Will this technically fit in my board? And you will not know that from a Spice simulation.
Got it. So this design as it is works, printed with Squink. You can send this out to Advanced Circuits or anyone
Indeed.
else. And this would be exactly more or less what you get.
Once we had it working perfectly, and technically we have a machine that just runs on this power source, we knew that it was safe to integrate into the main. So we have like this version system, so we essentially integrate it into a release version. So we know that this is stable, and we can start integrating into the final version.
So this works into an electrical engineer's typical workflow. It just replaces or supplants the existing method where you send the board out, essentially.
It does. It does. I would put it simple. It does three things for you.
Okay.
One is, if we didn't have this method of reproducing a board, right? We would have designed it, in a breadboard, and they will have like cables coming out from everywhere, and then we'll plug them into the board, right? Because it's the only way you can technically turn that board on, right? You have no other source of power, so you definitely need to have a power source that replaces the one that is not working.
Got it.
So you could do that, but then you're exposed to, if you move the machine, then a wire comes off, then it gets disconnected, whatnot. So what oftentimes happens is that you're at a point where you have tested it and you know that it works. And since you could either just manufacture this little board, right, and it will cost you 40, I'm talking just the bird board, right? Or you could manufacture the larger board and it will cost you, I want to say 70, right? You're at a point where your only choice is, okay, why don't I just create the large one? The difference is $40, but I'll be closer to my final design, right? That is what you would have if you didn't have a way to create a board like this that will do the third thing for you, which is not saving time and money, is that gives you the peace of mind that you have built it the way it should have built, the way it should have been routed, and by the time you integrate it in the final design, you are sure.
So failure is an option, in other words.
Yeah, obviously,
Because
because you design it right, like you know you have simulated it in the breadboard, but at that point you haven't even laid it down into the PCB, like you haven't actually decided where your components are going to be. So all you have is like this bunch of wires coming out and connecting each other, right? And then you take that and you translate that into your design in KiCad or whatever CAD tool you're using. And up until that point, you're pretty much hoping that that system is going to behave exactly the same as when you had it all wired up, right? But it may not. It may have more noise. It may be too close to another device that is producing noise, or it's consuming more than it should. It doesn't have enough capacitance, so it may not have enough decoupling, all those sort of things. This gives you a real idea of how it will behave once you have it on the board.
Yeah. So if I was actually to take a design that was similar like this and try printing with Squink, would I actually be able to succeed if it actually met the standards that we set out, like 1010 with trace widths or something like that?
Yeah, I mean, definitely. I mean, I can tell you this design is exactly the same design, the same layout that we use in the final board.
Oh, okay.
So it's essentially, it's kind of as if we had cut like a piece of the design, put it aside, modify it, fix it, and put it back.
Okay. It's a strange form of modularity, at least in that aspect.
Exactly.
It's great.
Now we have done the same exercise with other parts of the circuit, and I am not implying that's the best or even the most advanced way to do it. What I'm implying is that we are coming and comparing against software by the fact that you can produce things faster. You are allowing to create rapid prototyping, which in the end allows you to modularize and kind of do small steps towards the final goal. Right?
Yeah.
Which before was like an all or nothing. Like I design everything, I give it a blessing, and I send it for manufacturing, and then I get it back and I start seeing what works and what doesn't.
So you're trying to prevent heart attacks in electrical engineers.
you're trying to lower the chances of failure. Yes.
Oh. We really can. I mean, it is actually a real problem. With 3D printing, even with really complex prints, I'm more on the 3D printing physical side. You never know. And getting that print done was always difficult, like 3D prints, like physical plastic ones. But I talked to a guy who was a lot older than me, and he'd been like doing like plastic molding and things of that nature, and he said it was even worse 20, 30 years ago because you had to mill block of steel and then make one. Like, are you kidding me? I don't even want to do that. So it was actually even worse. I mean, you're talking tens of thousands of dollars just for one. And then you come across customers who are like a customer I met about a month ago who said he literally spent $40,000 on one round of prototyping for a single day turnaround. And I think it was 10 boards. I just wish I had met him earlier. I could have sold him a few machines. Because I was just like, he didn't really have the heart attack problem because it was the client who wanted it. But I imagine for a lot of smaller companies where, like us or other companies out there, where quite literally this is a large percentage of our budget has to be spent on one board. It has to be done right.
Yeah.
So I mean, but the electrical engineers who've gone through the iteration process, being very, very careful, what do you say to them? Because there's a few people I've met who are like, look, I don't have this problem because I'm very diligent.
And that's the best way to do it. Like we didn't fail on purpose on the design of the first power source. Like we actually made our simulations. We were sure it would work. And then we realized that one component in the board wasn't good enough at lower amperage, so we needed to swap that component, but we knew the next one would take more current, and we're kind of hoping the power source will keep up, and it didn't, right?
Oh, okay.
So it's like you are trying to, as you move forward in your design, you are following essentially protocol, you're defining specs, and you're following specs. Right. And there's a point where you just need to make choices because you know that actually making a little bit step on the side from whatever has been decided from the beginning of the project will allow you to be more flexible or maybe reduce certain problems in the future. So sometimes you just have to take those decisions, and that's when you kind of find yourself against the wall and say like, oh, okay, I need to redesign the whole thing, or I could just try to break some lines and make this change here, right? But I believe in the end, the part that brought us the most joy about like creating this board is the fact that we weren't dead in the water for 10 days, right? Like we were like, okay, we have this problem. What is the solution?
Yeah.
And June started hypothesizing on like, oh, we could do this. Oh, but then we'll have to redesign this and that.
I think it
was like, hey, this needs to be higher. Let's test 2 or 3 designs.
Uh-huh.
Let's find the one that gives us like the cleanest voltage output at high frequency, so we can provide like higher currents and stuff. And all right, let's go at it, right?
And you made an iteration, I think, before we used different ones, the tantalum capacitors instead of the electrolytics before they arrived, things like that. So, you were like, it was Anthony. I think he was like designing on the fly. He was just using whatever he could find.
Yeah, exactly.
He used the 233 Henry inductors. So that's why the photograph looks different from what we have here, is because we actually got the parts in the intervening time. And I think we tweaked the design just to use these parts that we actually received, so we get a cleaner signal. So it's kind of like leftover circuit board making. Kind of use whatever parts you have sitting around. It's like leftovers. You kind of put it together, and then you got something to eat. So that's kind of the critical thing, and that's why we're sort of really big on this. Trying to fit into the people's value chain. I like that idea the most. I think the fact that people can design something and be sure it works, and they can actually just send it out on a large scale. Some people are asking me, can I make like hundreds of boards? I'm like, well, with this machine at this point, it's not our focus, because you can get that board made elsewhere. Absolutely. People come back to us and say, I can get a board made for whatever, $40 for this or something like that, and it takes a week or two. But sometimes you just don't have time.
Yeah.
Right? So for ones where you need the time, just one board, I need it now. This is where the product like ours fits in. So
yeah. So that's kind of the story of the little one, and we expect to keep doing this kind of development. But because what we found is that it allows us to take the sprints, which is what we call the cycles for review of our design and our progress in the project, actually to have the time that it was before, right? Because we can always, go get over the trouble that we find the way just to go to the next step, right? Like it's not like, okay, I have 2 weeks to get this done, and on day 7 I just hit a wall. I'm like, oh, I have to send this again. So okay, it's definitely not going to happen by Friday. Yeah. You know that there's a way it may happen by Friday.
Yeah.
You just have to, now you kind of deviate your resources, you design a little bit more, you print, and you're back on track.
Awesome.
So, right?
So back on track. All right, I think you have to get back to work. So
have to go. So I mean, I'll be in the loop. So if you have any questions or suggestions, I guess.
Yeah. I'm just gonna go over the last part, which is the pick and place. We've already gone through the printing and dispensing, but there's some things, tips and tricks in pick and place that we've been sort of hearing from people. So we just want to talk about that and go from there.
Perfect. All right. Boom.
See you around.
See you later.
Okay, so that's Carlos, and so let's get to the next step. So if you look at the video right over here, you can see, I'm just going to move this, make it a little bigger. So while this video's been going, we've done all the printing, we've done all the pick and place, dispensing, and now we're actually going down to pick and place. And if you notice in the video on the middle left, basically I've zoomed in and sort of cropped, or included in the crop, essentially the board and the tray, and most of the components are there. One question I've asked myself and other people have asked is how you actually know what your zero rotation of each component is. We do describe in the software, you can see right here, the part orientation essentially is pin 1 to the left. But it really depends on the user himself or herself and how they actually design their design in their CAD tool. If you see the 2 windows on the right, essentially what I've done is I've essentially just turned on KiCad, and I have the footprint editor. And basically what I've done is I've sort of right-clicked on the footprint, that specific part, to look at the footprint editor and to see what the components zero rotation is going to be. Once I know that, essentially I know what the part is supposed to be oriented as on the tray. For some people, they take the bomb sheet, they look at the rotations that are actually inserted into the Squink. For example, 270 degrees right-hand turn, it's going to essentially be the same as negative 90. So it's important to note that our machine just takes 270 and makes it negative 90, essentially rotating in a particular way. So it's very important that you might have your CAD tool open while you're using pick and place to determine exactly what your zero rotation is, so that your part gets placed correctly. There's nothing worse than placing an LED diode backwards. So from that, I just wanted to sort of describe that. In the tray you see right here, I've done essentially lined up a bunch of components. Most of those are 1206s. I have a number of 0805s. And essentially what I'm basically doing is I'm just essentially guiding them into the bottom right corner of that slot. And making sure that, at least for the passives, they're just essentially oriented like I described. I looked at the CAD tool, I looked at the footprint editor, determine which way they were oriented. Most passives, in fact, nearly every single passive I run across is oriented sort of long side facing down, sort of basically matching the shape of the slot. But occasionally, you never know. You might want to take a look at your footprint editors before actually putting in your components in the tray correctly. At this point, at least in this process, the machine is going to be picking placing components that are smaller, that don't require what we have a suction cup. We actually have small suction cups that we've included with each machine. For picking and placing these components, you don't need a suction cup. For the larger components that you see on this board, like caps, the switching, these MOSFETs, your inductors, even your Schottkys, your diodes right here, you may want to use these suctions. And we have two types of suctions, a small and a big one. The big one is a bit of an overkill for most components. You can lift these heavy, these are 68 microhenry inductors, relatively easily with the smaller suction cup. But these passives, like a 1206, you can lift it with a suction cup, no problem. But it's going to essentially completely almost envelop the components. So you have to take off the part, click on camera, make sure it can identify the tip, put it back. And when you put the suction cup on, you should go click on camera and re-identify the tip so that you know that Squink knows where the tip is. Without knowing where the tip is, it's going to be placing the components incorrectly. So there's another thing that comes, at least in this part of the video, that's pretty interesting. So while I was realigning or placing the camera shield, it's basically a green shield that essentially acts as the world's smallest green screen, helps us identify the edges of the parts when the camera takes a photograph. A little bit of conductive glue got on my fingers, and then got onto the pick and place camera shield. So essentially, what's happening, if you look in some of these pictures, so I have the camera video feed visible on the software page. It kept on identifying a smudge of silver ink, which is shiny and perfect thing for the machine to think is a component. And so it didn't place the components incorrectly. So we've gotten to the point now where the machine knows that this is not the components it's looking for, and essentially returns them back to the tray. So I saved myself the hassle of picking and placing the component in the wrong spot and having to remove it and put it back in the tray. Squink kind of basically said, this is not right, replaced it. Did waste a little bit of my time. I was trying to think of what the heck the problem was, and I looked at the video feed and we can see that the machine was identifying the green box around the smudges on half the components. So for a brief moment, I think I take off the camera shield, go over, find some IPA, clean it as off as best I could, and I basically completely cleaned it, scrubbed it off, put it back on, and then did the components that didn't place properly. And so if you're seeing this issue, make sure that your camera cap is completely clean. You'll be able to see that it's not identifying the components pretty quickly. But this is the first time I've ever noticed it, so I'm not sure if maybe other customers have seen it. beyond that, I think we have a pretty good, so far so good. I mean, half the components that were placed correctly, with the correct orientation. Does anyone have any questions on the live chat? I know there's some people out there. I'm not sure if I'm coming through clearly. Hopefully my voice came through. If you have any questions specifically for Carlos, you can always email us at contact@BotFactory, and I will actually get through to him or forward it to him. Okay. So a few other people are asking questions about dispensing, and we unfortunately passed through that part while we were talking to Carlos. But I kind of wanted to raise a few points about dispensing. This is the, I can just move this board, show you a little bit about what I'm talking about. So this is the glue packages that come with each machine. It essentially consists of a hardener, which is this clear liquid, and a resin, which I believe is the silver stuff. It's basically full of silver particles, and you mix it by taking, here's a finished one, but if it was separate, there's a small barrier. You essentially force it up against a surface, like a corner of a surface, like a table corner. Break it through, rub it, and back and forth, moving the material up and down through the package until, let's say, 40, 50 times. If you don't mix it enough, we have found that some of the clear material separates from the silver epoxy, and so you might be dispensing one bit instead of another bit, and you won't get perfect connections between the component and the traces. So to that point, people have actually been, at least I've been noticing this, and I just wanted to make it clear. It's very important that you mix this stuff as well as possible. Another thing people have been asking, so we have this new head change. So new head change. So we've changed the head design to fully envelop the syringe and hold it straight. Because on larger boards, what typically happens is the syringe bends a bit. If you're having issues like this, please contact us at support@botfactory.co, and we can help out there. Okay, so what's going on here? Right, so when I was talking about making sure that your nozzle tip, if you put a suction cup on there, is placed correctly, this is what I was talking about. You see on the left-hand side of the screen when you're on the placement page for putting the components in the tray, selecting slots, etc. Click on that camera, and it will basically send you back. That functionality is really important. Otherwise, Squink might get confused about exactly where the tip is. So at this point, I have placed these guys, your MOSFETs. I placed it in slot 15, which is the biggest slot we have. And these components have to be oriented, you can see in the KiCad view on the top right, have to be oriented with basically the pins facing the bottom right and the heatsink facing the bottom left. That's the orientation on the KiCad, therefore it's the orientation on the tray. For some people who've been asking, why can't I place these components in, let's say, slot 0, 1, or 2, which is on the left-hand side slots on the tray, simple reason is that the machine will essentially trigger a switch on the right-hand side. The head goes too far to the left, triggers the switch, and then stops working. In earlier iterations, we discovered that placing the MOSFETs in the tray from 0, 1, 2 would cause this problem because the parts were too wide. We've determined that depending on how you've essentially where the component is, where the tip has been found on the camera, basically determines how wide the part is. But typically, try not to use a component bigger than 10 millimeters in width. Anything longer, so if these MOSFETs, for example, the longest length is 14. But these inductors, you see here, this big guy, 68 microhenry inductor, is 10.25 millimeters. And that was, I could pick and place that guy. So anything above 10, 10.5, 11, you're going to run into trouble. And the way it looks, essentially what happens is the machine picks the component and then immediately stops. Because what has happened is essentially it's going to give it a trigger, a switch basically, and then stop. It says wait, you're on the edge, stop, just basically stop everything. And the only way you can get out is basically by canceling your print and starting from the beginning by re-uploading your files. I've seen a few customers with this problem, just one really. So I just wanted to warn you, at least in that case. What else have we discovered during this pick and place function? That's about it. Someone was asking me a few days ago whether or not they can use different tips with the dispensing function. So, yes you can. Yes you can. So, the cool thing about our syringes, this aside, is that they are medical grade. They are basically found more or less anywhere, although we have designed our head to work specifically with these syringes. But the ends of the syringes are what they call luer lock, L-U-E-R, luer lock. It's a specific type of pitch, thread width, diameter, that is commonly, like a series of different widths. But long story short, it basically means that one tip like this, can be used, as well as tips like wider diameter, thinner diameter, longer length, etc. And they can still be fit onto our syringe. So, if you're using, let's say, a thicker material, let's say you're using something much more viscous, solder paste, for example, you may want to consider finding tips that are wider or have a larger diameter, larger gauge. These are gauge 23, I believe, and try those out. At a certain point, the linear motor on our glue head is going to be unable to push material through. Laws of physics being what they are. So you can't really force it through anymore, so you potentially don't get any dispensing. So we do recommend to some people that they try larger diameters. Of course, the problem is that you're going to have a larger dot size. So there's other options. If you have solder paste, there's ways of thinning it. Some people have been considering about how to do that. There's a lot of information online. There's other manufacturers for solder paste to make the material a bit thinner. Thinner it is, of course it might drip through, but you get finer dots with these tips. So yeah, that's one thing people have been asking. I think a few other things that I've been noticing recently. I'm getting much better results in terms of printing my insulating layer when I basically take my IPA, which comes with each insulating ink cartridge, and apply a little bit after I'm done printing. A few people, basically the reason is that the way thermal printing works is essentially there are a chamber with a small resistor or heater, as I like to call them, that essentially creates a bubble, basically heats up, creates a small bubble, and forces a liquid through a small aperture, which is seen right here. It's this guy right here. Well, there's 12 of them, to be specific. One of the problems with using heat to essentially move material straight out of a nozzle, it's small, it's in the microns, is that the heater itself gets covered with materials. So we found that applying IPA essentially helps clean these chambers and these heaters and prevents them from essentially, it keeps them operating at higher efficiency. So you get more flow and therefore no problems. So that's one thing that I'd like to keep in mind. You do not need to cover up the nozzles when you're done. You do not need to refrigerate the insulating ink cartridge after you're done. But it's best to keep it in this container, in a sort of drawer or anywhere that's away from large UV sources, aka the sun. This is a UV curable ink, so that functionality is kind of important. We keep it in the liquid state. So here I am placing large, I think I'm placing the Schottky diodes. They don't need any orientation, they come this way. We're picking and placing these big ass electrolytics. These are 470 microfarad electrolytic capacitors. And I'm very sad because unfortunately that one component fell over. The thing about large components is, let's be honest, you don't necessarily need the machine for like a bipolar gap. And essentially, you pick it up, move it into place, and then be done with it. Of course, manual functionality being what it is, we have that option to essentially allow you to do sort of very fine, tiny parts, as well as large parts that are difficult to place because there's other components around. It's got a very tight key. The keep out is like neighboring other keep outs, so it's going to be very hard to place very easily. Things of this nature kind of lend itself to the possibility of using the manual function. So we included a manual function for a number of reasons users were asking for it. It also made a lot of sense from our own perspective. Tiny components are difficult to place by hand, and the machine being what it is in terms of high quality resolution, it's difficult to pick and place very small components at this point in time. So manual functionality allows you to pick and place sort of the oddball components that you might come across. So it's on the left-hand side. You can hit that button, and essentially what you can do is you can manually pick up a component and then manually place it wherever you want. Each step is anywhere from 50 to 100 microns. You can get very high quality stepping in terms of trying to find a position and place it. I've pick and placed, manually speaking, a QFN. I've pick and placed an O201. It did take, let's say, longer than an automated system, but it was quicker than using anything by hand, by a country mile. I can't tell you how difficult it is to play an O201, where sneezing is not an option. I mean, this stuff you can inhale if you're not careful. I think at this point I pick and placed, I think I tried pick and placing these components again. And I think this time I succeeded. Key thing to know, very important thing to know. When you're pick and placing a board like this, let's take a look. When you're trying to pick and place a board like this, think about the actual height of each component. These caps are easily 1.5 centimeters tall, which is actually beyond the distance between the bottom of the tip and the top of the camera shield. So basically, if I'm picking and placing these giant capacitors, and then I'm picking and placing my 0805s later on, I'm basically going to knock these guys over if I'm not careful. So typically, this is a very important thing. If you have a board like this, it's very important that you pick and place the smallest components first, and I'm talking small in terms of shortest components, and then gradually go higher and higher and higher so that your largest components are placed last. You can do this in a bunch of different ways. You can essentially place your smallest components in the first 0 to 1, 2, 3 components first, or you do what I do, which is basically do all the small components at once. They're typically the hardest ones to place, and then I pick and place larger ones as I go along. And that's exactly how I built this board. At this point, I believe I actually finished the run, and I think, yes. What happens is I just eventually just place the small components and then go to the final stage, which is heating. A few people have asked me how long it takes to cure the glue. 10 minutes at 100 Celsius is typically all you need to cure two-part epoxy that we have. It will cure itself in 24 hours. The heating process basically just essentially accelerates the process of curing. And in doing so, you might actually heat up components. I recommend taking a look and see if your components can withstand 110 Celsius. Typically, these are S&D components that go through heating, or they are soldered, so of course they can withstand these temperatures, but you never know. So sometimes you come across electrolytes and may not be able to actually withstand that kind of stuff, but soldered or something like that. Long story short, try to keep it around 10 minutes. I've cured stuff in 5 minutes. Typically enough heat to essentially sort of give it a set, but complete curing should take no more than 10 minutes at 100 Celsius, 110 Celsius. These are the 100 microfarad. So these components are extremely light, and I noticed that when I was picking and placing them, that there was a little bit of jiggle, but generally speaking, the components were fine. I was a little concerned about one of them, so there we go. Yeah, so I removed these components and I tried them again. I think what I did is I applied more glue later on and then I did it. Yeah, I just basically, if you want to go to the next step for the final process, you just simply click next and there you go. So the heating, yeah, that's it. Okay, so, any more questions? Any questions on the live chat? Okay. There being none, I think we can close this up. I'm going to be doing some more thinking about more application webinars we'll be doing. I'm definitely thinking about doing a more detailed explanation of how to dispense with Squink in certain variations using conductive glues as well as solders. Some people have been asking that question. Hopefully there's been enough detail in terms of how to pick and place with Squink. But I'm definitely welcome to hear more questions. If you have any questions about our power source or anything like that, tell us here or email us at contact@botfactory.co. If you have any support questions, contact us at support@botfactory.co. Not .com. This is JF signing off. Really appreciate you guys coming by. Yeah, hope to see you again. Yeah, if you have any questions, if you're thinking about buying Squink, you can contact me at sales@botfactory.co as well. Thanks a lot. This video is going to be up on YouTube, so you can basically share it with anyone you would like. And let us know what you think, how we can do a better job. Thanks a lot. Have a good day.